Today we are going to discuss about Johnson counter. It's also known as creeping counter, twisted ring counter, walking counter, mobile counter, and switch tail counter. This is an example of a synchronous counter. In a Johnson counter, the complemented output of the last flip-flop is connected to the input of the first flip-flop. We know that this is a counter that is obtained from a serial in, serial out shift register by providing the feedback from the inverted output of the last flip-flop, that is the complement output of the last flip-flop, to the D input of the first flip-flop. So the output of, here for example, is here. Here is a figure shows a 4-bit twisted ring counter or Johnson counter using D flip-flop. Here there are 4-bit, it's a 4-bit Johnson counter, so it requires 4 flip-flops. And here the last inverted output or complemented output, this is the output of the last flip-flop, this is the complemented output or inverted output of the last flip-flop, which is connected to the input of D input of the first flip-flop. What is the difference between ring counter and Johnson counter? In the ring counter, the output of the last flip-flop, that is here, this one is connected to the input of the first flip-flop. So here it is inverted output is connected to the first flip-flop. Then here the Q output of each stage is connected to the D input of the next stage, but the Q bar output of the last stage is connected to the D input of the first stage. Therefore, its name is twisted ring counter. This feedback arrangement produces a unique sequence of states. The same using JK flip-flop is shown here. In this figure, we know that the Q bar output is of the last flip-flop is connected to the J input of the first flip-flop, and the output of the last flip-flop is connected to the K input of the first flip-flop, or remaining stage each output is connected to the input of the next stage, and inverted output is connected to the K input of the next stage. And it is a synchronous counter, so single clock pulse is applied to every flip-flop. So, and it is a negative edge triggered flip-flop, so is a single bubble is given to that input of this clock, so it is a negative edge triggering flip-flop. So to implement a n-bit Johnson counter, we require how many flip-flops? We require n flip-flops, and it is a shift register counter. It is a shift register counter, and the number of used and unused state in n-bit Johnson counter. For a used state, for a n-bit Johnson counter, the number of used states are 2n, and for number of unused states are total states. For a n-bit counter, there are total states are 2 raised to n states, and here unused states are 2n. So what will be the unused states? 2 raised to n minus 2n. This will be the unused state. So used state means total state minus used state. How to find out the unused state? Total state minus used state. So total state for an n bit is 2 raised to n. So used state is 2n. So subtract both. Then we will get the unused state. The figure shows the state diagram. State diagram initially is starts from 0 0 0 0. Initially all outputs are 0. Then next state will be 1 0 0, and next 1 1 0 0, then 1 1 1 0, then goes to 1 1 1 1, then 0 1 1, then 0 0 1 1, then 0 0 0 1, then again it goes to 0 0. So after each clock pulse this sequence will be continued like this. So 0 to 9, total 10 stays after clock pulse it will regains again to initial state, or after 8th clock pulse it will be regained to the initial stage. So this is the sequential table. Then we can explain with diagram here. Using D flip flop. Here initially all flip flops outputs are 0 0 0 0. So Q4 is 0, then what will be the output? Q bar. Q bar will be 1. So this is the initial clock pulse, 0th clock pulse. Then what will be the first clock pulse? After first clock pulse, this 1 will be, after the first clock pulse, this Q bar will be given to the input of D1. So its output will be, D1 will be now 1. Then so now output will be 1. Then here previous case D0 containing 0, so it will be 0. Then again this output will be 0. Then Q4 output will be 0. Then third clock pulse, what will be happened? Here it is a shift register. So shift counter, each time the output is shifted to next stage. So next clock pulse, this again Q4. Q4 is equal to 0. So Q4 bar will be 1. So that 1 will be outputted here. That is input of here again 1. So 1 is outputted here. Then this previous 1 is shifted to here, and this 0 is shifted to here 0, and again this 0 is shifted to here 0 0. Then next after next clock pulse, what will be the output? That is again this 0 is shifted to here, and this 1 is shifted to here, this 1 is shifted to here, and here last case is 0 0. Complement of cube bar is 1. So here 1 is here, so here output will be 1. Output will be 1. So 1 1 0 will be here. Then on the next clock pulse, here 0 0 complement of q bar. Q bar is 1, so that 1 is here. So this 1 is shifted to here, and this 1 is shifted to here, and this 1 is shifted to here. So this last 1 is here. So now all are 1. Outputs are 1 1 1 1. So it start from 0 0. Initially it's 0 0 0, then 1 0 0, then 1 1 0 0, then 1 1 1 0, then next all are 1. Now all outputs are 1 1 1. So what will be the next? This 1 is shifted to, this 1 is shifted to here, so it is 1, then this one is shifted to here, it is 1, then this one is shifted to here, 1, then what will be here? This q bar, here it is 1, so it is 0, so that 0 will be here, so that will 0 is here. So now output becomes 0 1 1 1. On the next clock pulse, here output is 1, so complemented output will be 0, so that 0 will be here, D input. So this input will be shifted to here, it is 0, then 1 will be shifted to here, and again 1 will be shifted to here. Here last 0 will be shifted to here, passed to here. So now 0 0 1 1. On the next clock pulse, again this one is shifted to, 0 is shifted to here, this 0 is shifted to here, then this 1 is shifted to here, 1, and here instead of 1, 0 will be fed back to here. So now is 0 0 0 1, and on the next clock pulse it becomes all 0 0 0 0. So it is reached the initial stage. So this sequence will be continued. So this is the Johnson counter. So this is the sequence table here. Initially on the 0th clock pulse it is 0 0 0. Then on the next clock pulse 1, it is 1 0 0. Then this 1 is shifted to here, this 0 is shifted to here, then 0 is shifted to here, then complement of inverted output of the last flip flop is here, that is 0 in the inverted input ennu parayunnathu 1, so 1 1 0 0. So next 1 1 1 0, then 1 1 1, then again the complemented input of last will be given to the first input. So inverted input of 1 is 0 0, the remainings are shifted to right, so that is 0 1 1 1. Then 6th clock pulse it is 0 0 1 1, and 7th clock pulse 0 0 1, and 8th clock pulse again it reaches initial stage. Then this sequence will be continued, and the corresponding timing diagram of the clock pulse is given here. Initially the clock pulse are given and it is negative edge triggered, and initially q1 is first one, q1 will be 1. Initially all are 0, initially we set all are 0, then after first clock pulse q1 will be 1, then 0. Then during the next clock pulse q1 will be 1, q2 will be 1, then remaining all are 0. Then on the negative clock pulse edge of the next clock pulse q1 will be 1, q2 will be 1, and q3 will be 1, and q4 will be 0. Then next to negative edge of the clock pulse all will be 1, negative edge during the negative edge. Then q1 will be goes to 0, q2 will be 1, q3 will be 1, q4 will be 1 on the next clock pulse. At next edge q1 and q2 will be goes to 0, q3 1, and q4 1. Then next on the next clock pulse q1 0, q2 0, q4 0, and q3 0, and q4 will be 1, and the next negative edge all will be 0, and this procedure will be continued, or this sequence timing sequence will be continued for a Johnson counter. So that's all about Johnson counter.